Hi, welcome to the fifth trigonometric tutorial titled The General Solution. In today's tutorial, we will be looking at what the general solution is and why we have such a section. In terms of what you need to know, you need to be familiar with your grade 10 work on trigonometry. You also need to have gone through the first 4 trigonometric tutorials. I want you to think about the following. If I said sine of x is equal to 0,5, what is x equal to? You'd very easily be able to tell me x is equal to 30 degrees, right? Almost. 30 degrees is one of an infinite amount of possible answers that you could have given me. Think about this. Sine of 150 degrees is equal to 0,5. Sine of 390 degrees is equal to 0,5. What about sine of negative 210 degrees equal to 0,5? The different possible answers are endless. Hence, we have developed a thing called the general solution. Let us go through that. We are now going to have a look at general solution. General solution, now you'll notice here that I've drawn the trigonometric graph sine of x. This is the graph f of x is equal to sine of x. Right? And we are going to look at what x values we can have when f of x is equal to a half, or rather when sine of x is equal to a half. Now, special angles will tell us very simply that in order for sine of x to equal a half, x will have to equal 30 degrees. Correct? Well, almost there. Let's write this over here. X, we know that if sine of x is equal to 0.5, second function sine of 0.5 is going to give us 30 degrees. Is that correct? Like I say, almost there. There's only one slight problem with that. Let's look at when sine of x is equal to a half. That's going to be somewhere over there, right? Now let's draw a line across there. The different x values are going to tell us where sine of x, now this is the graph sine of x, hence wherever sine of x touches this blue line that I've drawn is where sine of x is equal to a half. Notice something. There's a lot more solutions than just 30 degrees. There's 30 degrees. There's over here which is going to be 390 degrees. There's over here and over here which I'm not yet taking into account. In fact, I will. This one is going to be 150 degrees. This one here is going to be 510 degrees. This here, by the way, is 30. This point here is equal to negative 210 degrees. This point of here over there is equal to negative 330 degrees. So I've got a number of different values, and notice that my sine graph is going to just continue in this pattern to positive infinity and to negative infinity. So when sine of x is equal to a half, there's a lot of different angles that x could be. But let's look at this. What's the relationship between 30 and 390? Isn't there a difference of 360 degrees? Because the graph, the sine graph, repeats itself every 360 degrees. So to get to 390, I could say plus 360 degrees. But I could also go negative. I could also go negative 360 to give me negative 330. So I'm going to say that x is equal to 30 degrees plus k times 360, where k is an element of integers. That means that k could be positive 1, k could be 0, that will give us 30 degrees, k could be positive 1, that would give us 390 degrees, k could be negative 1, that would give us negative 330, and k could have any other integer value. But that only accounts for those values. What about those other three values? Now remember, when we sketched our 30-degree angle on the Cartesian plane, we sketched it either there, but it could have also been over there for sine of x to be positive a half. That angle is in the second quadrant, which means that x will equal 180 degrees minus 30, which is the same as 150 degrees, which would account for that one, plus 360 minus 360, so it's 150 degrees plus k times 360 degrees, again where k is an element of integers. That there is the general solution. So when sine of x is equal to positive 0.5, x could either equal 30 degrees plus k times 360 or 150 degrees plus k times 360. And that's because the sine graph repeats itself, or rather the sine function repeats itself every 360 degrees. The general solutions for sine and cos are both plus k times 360. So for cos of x, if cos of x is equal to something, it means that x is either equal to, let's say cos of x is equal to root 2 over 2. We know from special angles that this means x is equal to 45 degrees, but it's going to be 45 degrees plus k times 360, because the cos graph also repeats itself at intervals of 360 degrees, where k is an element of integers, or x is equal to, now where else is cos positive? In the fourth quadrant. So it's 360 degrees minus 45 degrees plus k times 360, again where k is an element of integers. We can simplify 360 minus 45, we can make it 315 degrees. Now, if cos of x were to equal negative root 2 over 2, we know that when cos is negative, in which two quadrants? Quadrant 2, which would be 180 degrees minus 45 degrees plus k times 360, or quadrant 3, which would be 180 degrees plus 45 degrees plus k times 360, both of these where k is an element of integers. And again, that can be simplified into 135 and this into 215 degrees. So that is working with general solution. Both cos and sine repeat themselves at an interval of 360 degrees. Tan is slightly different. Tan of x let's say we're working with 10 of x is equal to, let's say 12. Second function, in fact, let's make it complicated, negative 12. Now, second function 10 of negative 12 on your calculator is going to give you an answer of negative 85.23 degrees. Work with second function 10 of the positive 12, which will give you an answer of positive 85.24 degrees. Let's just say 85 degrees. This is called our reference angle. Now, we are looking for when 10 is negative. That means that x either lies in the second quadrant, which will be 180 degrees minus 85 degrees plus k times, and I'm going to finish that off now in a second. The other quadrant where 10 is negative is in the fourth quadrant, which is this, either can be 360 minus 85 degrees or just 0 minus, but let's work with 360 minus 85 plus k times. Now the sine in the cos were k times 360 because the sine in the cos graphs repeated themselves at intervals of 360 degrees. That means that at every 360 degrees they were exactly the same. They repeated itself once at 360 and at negative 360, and it carried on like that. The 10 graph, however, because of its asymptotes, you'll notice that the 10 graph repeats itself at every 180 degrees. That's negative 90, positive 90. So the 10 graph repeats itself at intervals of 180 degrees. Again, this is where k is an element of integers. That brings us on to the general solution. If I had to say sine of theta is equal to a value, that means that theta is equal to an answer, or rather the second function of that value, which is otherwise known as our reference angle, plus k times 360 degrees, where k is an element of integers. Or theta is equal to the other possible answer. Remember that sine theta, if it's equal to a positive answer, it means that theta lies in either the first or the second quadrant, whereas if it were equal to a negative value, it means that theta is lying in the third or the fourth quadrant. There are always two quadrants available. So the other possible option in this case is that theta is equal to the other option, which is our axis plus or minus our reference angle, plus k times 360 degrees, again where k is an element of integers. The same thing works for cos. For 10, it is slightly different because the 10 graph repeats itself at 180 degree intervals and not 360 degrees, as is the case with sine and cos. Therefore, if tan theta is equals to a value, it means that theta is equal to our reference angle plus k times 180 degrees, where k is an element of integers, or theta is equals to the other reference angle plus k times 180 degrees, again where k is an element of integers. I now want you to have a go at the following basic examples. Press pause on your DVD player, and when you return, we'll go through it together. The first one I gave you to do read sine of theta is equal to 0,5. Now, this means that theta is equal to 30 degrees, and that's called our reference angle. Sine of theta is 0.5. That means that theta is either equal to 30 degrees. Now, the reason it's 30 degrees is because this is positive. This is in the first quadrant. So it's 30 degrees plus k times 360, or theta is equal to 180 minus 30 degrees, which let's just write that in as 180 minus 30 degrees plus k times 360, which is equal to 150 degrees plus k times 360 degrees. And these all happen when k is an element of integers. K is an element of integers. That just means it can be an integer value, 0, 1, 2, -1, -2, and so on in both directions. The next one says cos of theta is equal to -√3/2. Now, when cos of theta is equal to √3/2, we know then that theta is equal to, again, 30 degrees. This is our reference angle. But cos is negative. That means that theta is either in the second or in the third quadrant. Remember CAST. In quadrant 2 and quadrant 3, cos is negative. That means that in this example here, theta is either equal to 180 degrees minus 30 degrees, which is 150 degrees, plus k times 360, or theta is equal to 180 plus 30, which is 210 degrees, plus k times 360 degrees. Both of these happen when k is an element of integers. Number 3 says tan of theta is equal to 3. If I use my calculator, the inverse function tan of 3 is going to give me, rounded off, 72 degrees. And this is my reference angle. Now, because tan is positive, it means that theta is either in the first quadrant, so it's going to just be 72 degrees plus k times 180 degrees. Because it's 10, it repeats itself at intervals of 180, or theta is equal to, now 10 is positive in the third quadrant, which is 180 plus. 180 plus 72 is going to give me 252 degrees plus k times 180 degrees. Both of these happen when k is an element of integers. Number 4 says -2 sine theta is equal to 1.8. Now, with this one here, before we can get the general solution or any form of solution, we've got to get sine theta on its own. In order to do that, we're going to divide this side by a -2. What we do to one side, we do to the other. 1.8 divided by 2 is the same as 0.9. So that's sine theta is equal to -0.9. Inverse function sine of positive 0.9 is going to give me 64 degrees rounded off. rounded off to the nearest whole number. That is our reference angle. But sine is negative. That means that it falls either in the third quadrant or in the fourth quadrant. In the third quadrant, theta is going to equal 180 degrees plus 64, which is going to give me 244 degrees plus k times 360, or theta in quadrant 4 is going to equal 360 degrees minus 64, which is equal to 296 degrees plus k times 360. All of these happen when k is an element of integers. Notice that we are using basic reduction, and we're using x reductions, either 180 minus, 180 plus, or 360 minus. And in the first quadrant it's 0 plus, so we don't bother to put 0 plus, we just put the reference angle. The next one I gave you to do read 12 sine theta is equal to cos theta. Now this one is a bit of a tricky one because I've got a cos theta and a sine theta. Luckily, I don't have any plus or minus any other terms. What I'm going to do here is fairly different. I'm going to get rid of the sine theta on that side, divide it by sine theta. That means that cos theta will be cos theta over sine theta, or rather the right hand side will be cos theta over sine theta. Now cos theta over sine theta, if I were to invert this, would give me tan theta, because cos theta over sine theta, if I turn that into sine theta over cos theta, that's going to equal 1 over 12. That means that tan theta is equal to 1 over 12. If I use the inverse function tan of 1 over 12, that's going to give me an answer of theta is equal to 4.76. So I'm going to round it off to the nearest whole number, 5 degrees. That means that theta is equal to 5 degrees. This is our reference angle. It's positive, so it can fall in quadrant 1. That means that theta is equal to 5 degrees plus k times 180 degrees because it's tan, or theta is equal to 180 plus 5 degrees, which is 185 degrees, plus k times 180 degrees, and all of this happens when k is an element of integers. Number 6 says 5 tan theta minus 1 over cos theta is equal to 4 over cos theta. I'm going to start this one out by simplifying this side to make that 5 tan theta is the same as sine theta over cos theta minus 1 over cos theta is equal to 4 over cos theta. For this example, firstly I know that my denominator cos theta cannot equal 0. That means that theta cannot equal 90 degrees. But not only 90 degrees, there are other points that make this equal to 0. And I'm just going to write this in. This is my restrictions. Theta cannot equal 90 degrees plus k times 360. And that would make it undefined. Alternatively, theta cannot equal 270 degrees, again plus k times 360, for that would make it undefined. This is just our restrictions. Our denominators cannot ever equal 0. Notice that even our restrictions have got general solution in it. Now, I can get rid of my denominators by multiplying everything by cos theta over 1. That means that this will read 5 times sine theta minus 1 is equal to 4. That means that 5 sine theta is equal to 4 plus 1, which is 5. That means that sine theta is equal to 5 over 5, which is 1. That means that theta is equal to 90 degrees, and this is our reference angle. Our reference angle conflicts with our restriction, which means that there is no solution to this example. There are no theta values that will make this valid because our denominators will be 0, which makes them undefined. Not so bad, were they? I now want to move into a few more complex type of examples. These examples are going to include some constraints. I want you to have a go at this next bit of examples. Press pause on your DVD player, and when you return, we'll go through it together. The first one I gave you to do read sine of 2x is equal to cos of x. The problem with this is, in order to try and get rid of any of the functions sine or cos, they need to be the same function. For example, it's easy to say if sine x is equal to sine of 30, it's easy to say that x is equal to 30 degrees, right? But they have to both be sine, or they have to both be cos, or whatever. In this case, I've got sine and I've got cos. Now, sine 2x I'm going to leave as is, but cos of x I'm going to make that sine 90 degrees minus x. Because think about this, cos of 10 degrees is the same as sine of 80. So cos of x is the same as sine of 90 minus x. Now I can drop the signs, which means that 2x is equal to 90 degrees minus x. Problem with that though is we've still got to include general solution. Why? Think about this. I said that if sine x is equal to sine of 30 degrees, x is equal to 30 degrees. Correct? Almost there, but what if I had sine of 150? Isn't that the same as sine of 30? What if I had sine of 390 degrees? That's also the same as sine of 30. So I've got to include general solution. Because it's the sine function that we've taken out, my one option is 2x is equal to 90 minus x plus k times 360, where k is an element of integers. My other possible solution says that 2x is equal to, what is the other quadrant that deals with sine? The second quadrant, which would be 180 degrees minus 90 degrees minus x plus k times 360 degrees. Again, k is an element of integers. I can solve this. This means that 2x, take that x across, it's going to become 3x is equal to 90 degrees plus k times 360. 3x, I want x on its own. That means that x is equal to 90 divided by 3, which is 30 degrees, plus k times 360 divided by 3, which is k times 120. We've got to divide that into both of those. That's one possible solution. This is for quadrant 1. That's where k is an element of integers. Or 2x is equal to 180 degrees minus 90 degrees plus x plus k times 360 degrees. That x can come across. That means that that'll be 2x minus x, which is just x, is equal to 180 degrees minus 90 degrees, which is equal to 90 degrees plus k times 360 degrees, again where k is an element of integers, and this is the quadrant 2. The next one I gave you to do read sine of x over 2 is equal to cos of 60 degrees plus x. I'm going to leave the sine x over 2 as that. I'm going to turn that cos 60 plus x into sine 90 degrees minus 60 degrees plus x. Don't let the brackets confuse you. I'm still doing the same thing as previously, except now we've got a whole bracket there. This means that sine x over 2 is equal to sine 90 minus 60 is going to give me 30 degrees minus x. Minus times minus is, minus times a plus is minus. That means that x over 2 is either equal to 30 degrees minus x plus k times 360 degrees, or x over 2 is equal to, what's the other quadrant we work with sine? 180 degrees minus 30 degrees minus x plus k times 360. This is quadrant 2. I'm going to start by getting rid of that denominator. By the way, both of these are when k is an element of integers. I'm going to start by getting rid of that denominator. That means that x is equal to 60 degrees minus 2x plus k times 720 degrees. Minus 2x across means that 3x is equal to 60 degrees plus k times 720 degrees. Let's just take this off for now. That means that x is equal to 20 degrees plus k times 720 divided by 3 is equal to 240 degrees, where k is an element of integers. That's the one possible solution. That's for quadrant 1. If I look at the quadrant 2 solution, remember I said that the quadrant 2 solution is going to be when x is equal to 180 degrees minus that whole thing. So it's 180 degrees minus 30 degrees minus x plus k times 360 degrees. That means that that's x over 2. That means that x over 2 is equal to 180 degrees minus 30 is equal to 150 degrees. Minus times a minus is plus x plus k times 360. That means that x is equal to 300 degrees plus 2x plus k times plus k times 720 degrees. X minus 2x is going to give me minus x is equal to 300 degrees plus k times 720. That means that x is equal to negative 300 degrees plus k times 720. Why didn't I change that plus into a minus? Because k can be positive or negative, which means that there's no need to do that. And that's our quadrant 2 solution. Number 3 says cos of x is equal to sine of 150 degrees minus x. I'm going to start by making this cos of x, well, leaving the cos of x as is, but turning this sine of that into cos of 90 minus 150 degrees minus x. That means that x is going to equal 90 degrees minus 150 degrees plus x plus k times 360, where k is an element of integers. But that's only one possible answer. The other possible answer, where else is cos positive? Cos is positive in the 4th quadrant, so that will be 360 degrees minus 90 degrees minus 150 degrees plus x plus k times 360, k element of integers. This is going to be x is equal to 90 degrees minus 150 degrees plus x. Take the plus x across, it becomes x minus x is 0. So for here, x could be anything. X is an element of reals, or rather, for this one, we're going to say that there's no solution. Because we've got x, when it comes across, it becomes negative x, and a negative x minus x is 0, so the x's are basically cancelling with each other. That's only for that one though. There's also this solution here, which is going to become 360 degrees minus 90 degrees plus 150 degrees minus x plus k times 360. Minus x across makes that 2x is equal to 360 degrees minus 90 is going to give us 270 degrees. 270 degrees plus 150 is going to give me 420 degrees plus k times 360, where k is an element of integers. If 2x is equal to that, that means that x is equal to 210 degrees plus k times 360, again k element of integers. So there's only one real solution in this case as opposed to 2. The last one I gave you to do read 6 sine squared x plus 3 sine x is equal to 3. I'm going to start by making this 6 sine squared x plus 3 sine x minus 3 is equal to 0. This does look difficult. Look at this here. 6k squared plus 3k minus 3 is equal to 0. Now if I factorize this, 6 times 3 is 18. Are there factors of 18 that can give us positive 3? Yes, they are. We need to get to positive 6k minus 3k will give us plus 3k minus 3, 6k times k, 6k squared. That means that 6k minus 3 is equal to 0, or k is equal to negative 1. That this one here means that k is equal to negative 3 across becomes positive 3 over 6, which is 3 over 6, which is the same as 1 over 2. So k is either equal to 1 over 2 or k is equal to negative 1. But remember that k was sine of x. So this means that either sine of x is equal to a half, or sine of x is equal to -1. If I solve for sine of x being equal to a half, it means that x is equal to 30 degrees plus k times 360, where k is an element of integers, or x is equal to 150 degrees. Remember, second quadrant, 180 minus our reference angle. 150 degrees plus k times 360 degrees, all when k is an element of integers. But that's only two of the possible solutions. The other possible solution is when sine of x is equal to -1. That means that x is going to fall in either the third or fourth quadrant. So that means that x is either equal to 180 degrees plus, now second function sine of 1 is 90 degrees, so it's either going to equal 180 plus 90, which is 270 degrees, plus k times 360 degrees, or it's going to equal 360 minus 90 degrees, which by the way is also equal to 270, so we only need to write this one solution in. With k being an element of integers, that means that we've got 1, 2, 3 possible solutions. X could be 30 degrees plus k times 360, or 150 degrees plus k times 360, or 270 degrees plus k times 360. And that brings us to the end of the fifth trigonometric tutorial. Please note that this is an extremely important section in trigonometry. You do need to understand why we use the general solution and how we use it. It is also very important for the next section, titled the trigonometric graph. Before you move on to that though, I want you to have a go at the exercise that I left for you in the workbook.